Hello, my name is Jacob Callahan. I'm a quality engineer for Satellite 6, and today I'll be talking to you about testing smarter with containers. So first we'll start off with why containers. And these are 5 of the top reasons I can think of why you can and should be using containers for your testing practices. First, it's great for version control. It can be also used for packaging, used as a miniature VM, which is what I do most of the time. It can be deployed anywhere with the asterisk on there denoting that it can be deployed anywhere that containers can be deployed, which, as I'll discuss later, is quite a few places. And my personal favorite is you can use it for stress testing. If you're familiar with Huggy's presentations about what a QE is, you know that QE is basically Batman, and this is another great piece for your tool belt. All right, so we'll start off with version control. Container images allow you to take basically a snapshot of your project in its current state. And these snapshots can either be static or automatically generated. For static images, you can manually commit an image from changes made on top of a base. Basically what this means is that you start off with a baseline container, whether that be Fedora, Ubuntu, even anything from Python, Ruby, etc. You basically just start with a single container images, go into it like you would with a normal VM, and then make your changes on top of it, commit it for later, and now you've got a new image that you can start off right where you stopped. Additionally, you can create an automated build file known as a Docker file. This is pretty useful for having a consistent build every single time, that you don't have to keep up with your base image and make changes manually anytime that you want to push out a new image. You can also share this image out to the wide distribution of either the entire internet through DockerHub, or you can keep it locally when you export your images, at least through Docker, in the form of a tar file. And this is perfect for testing new code changes. Personally, whenever I make any significant changes to RZA, I will rebuild the RZA-based image, and I will run the test through that to make sure that nothing is broken. And it's great for having an isolated environment that I know that nothing is going on my local setup, maybe dependency-wise or what, that could have caused any of those issues. Okay, automated builds. These are my personal favorite way to build Docker images. DockerHub will build them from a designated repository. So for example, we have here on the right, Satellite QE has a DockerHub account where we have a couple different things, including Satellite Populate. So anytime that we push a change to Satellite Populate, whether that be from any different target branches or just a master branch, it'll recognize that, and it will build a new image to bring it up to the latest version that's on GitHub. This way, that if someone wants to use your project and doesn't feel like installing all of the dependencies and everything like that, they can just pull down the DockerHub image and then go from there. You can run multiple versions of testing frameworks from one machine this way. So for example, on the right, you can see that we have tags for 6.3, 6.2, and 6.1. Those are different versions of Satellite. So instead of having to manage different versions locally, like checking out a different branch, maybe updating dependencies locally in each virtual environment, you can just use individual images that are available through DockerHub, and then run against different versions of Satellite without having to worry about any peculiarities that may be going on between different branch versions. And perhaps better, So then this is that you have very easy distribution. Anyone with a Docker client that has a connection to DockerHub can just Docker pull, and they'll have your new image. As I alluded to earlier, using containers eliminates concerns about conflicting dependencies, and you can also release images in what I call product mode. Okay, so for conflicting dependencies, containers are isolated environments, which is really nice. On the right, you can see that I am pulling down the Python 2 image, and then we also have a Python 3 image available. This way you can build your project on type of both versions of Python and run them locally without having to worry about whatever Python version you have on that machine. So you can run Python 3 code, 3.6.2 in this instance, on a machine that only has Python 2.7. And for each container, you can pick and choose specific dependencies for each image. You can build it from Python 2 or Python 3 or whatever base you choose. And this way you can have multiple versions of the application with different environments. And it's really great for keeping your host machine clean. There are many dependencies that I have for some of my projects that are never installed on my local machine, mainly because I don't want to run the risk of breaking particular things, and I don't really feel like keeping up with virtual environments all the time. Additionally, you can run these images anywhere on your local machine without having to worry about moving into the virtual environment and then only running it from that location. Okay, so for single-purpose containers, or what I called earlier product mode, these images can be built to run only one command. This is what I do for RZA. It basically uses a keyword near the bottom called entry point. So the single entry point that's available for RZA is the RZA executable itself. And this makes it perfect for application packaging. Additionally, I have another image called genvert, which basically allows you to submit a vert.who report to satellite, and it uses the same thing. So what this means is that for a lot of containers, especially base images, you can do a Docker run and then get into a bin bash environment. That way you can basically use it as a miniature VM. But if you put it into product mode, as we'll continue to call it, then that's no longer an option. Whoever runs the container has to go through whatever command that you specified the container to run when it starts up. Again, on the right here, you see me trying to run bin bash through the RZA container, and then you get an output saying that it's an invalid argument because RZA doesn't accept bin bash as a argument. And then if you just check out the next line down there, you see I do RZA brute-h. Since I specified RZA as the command there, it will accept arguments then on. So you don't have to do Jacob Callahan /RZA and then RZA as the command. You can just continue on with subcommands. One thing that I do think is pretty useful here as well is if you do decide to go this route, and actually let me go ahead and pop over to a terminal real quick, and I'll show you what this Docker file looks like. So here I'm in the RZA environment. So let's view the Docker file. And down here at the bottom, you see the entry point says RZA. So that's the executable that's going to run. And then if they don't specify anything from there, it'll run the next line, which is command -- help, which would be appended to RZA to give help output. If you wanted to keep your container open so they can run bash, you would, instead of putting entry point, you can just use command again. All right, back to the presentation. Okay, so containers can be deployed on almost any system. And the great thing about this is that if it works for you, it works for everyone. And what I mean that containers can be run almost everywhere is that they can be installed on all major operating systems, as well as AWS and Azure. I'm sure the platforms just keep expanding because container adoption is exploding at a very quick rate. Docker already has an estimated 40% enterprise adoption with an additional 30% planning adoption. These are statistics I pulled from earlier in the year, so I'm sure that these numbers have already risen. And on the right, you can see an image showing the compatibility of different Docker versions against different platforms. Here you can see AWS and Azure are able to run both Docker CE for x86-64 and then the Enterprise Edition, as well as platforms available on Mac, Windows, and various flavors of Linux. Okay, since containers run on a standardized platform, and there's no need to install any particular tool or application or framework, there's nothing that a customer or other QE or developer can mess up when it pulls a Docker image or a container image. So that means that there's nothing that could have gone wrong during the quote installation process. So this means that someone can just download a container image and use it right off the bat. So you're not going to have to worry anymore about someone saying it works on my system just because they managed to potentially mess something up, or there might be something weird about their particular operating system itself. Here, all of that is abstracted away. It runs on one standardized platform, and you're good to go. Here in the example on the right, I'm running our automation tools, which is based on Python 2 on my local machine, which doesn't have any instance of Python 2 on it. So if I wanted to use this natively, I would have had to download Python 2 onto my local machine, whether that be through a virtual environment or just based on my operating system, and then worry about all that particular thing. But instead, I can just pull down the image, pass in the arguments, mount a directory, and I'm good to go. All right, one of my favorite uses for containers. They can be used as or thought of as a miniature virtual machine. However, they're much more lightweight than a traditional VM. So, as I said before, most container images are built on top of a minimal Linux distro. There are other base images that are available, really some even more exotic ones, but I believe there's also images available for different Microsoft products as well. And of course, like a Linux distro, you can get into a bash environment and you can install and configure the container much like you would a real system, and then commit that for later. On the right here, we have an example of me running a container image called ch-d rel74, which is a rel74 base image provided by Red Hat. In here, I'm just echoing command or echoing a string hello world to test.txt, catting it out, showing that it does indeed exist. And then I use v on the local system to modify the test.txt, which is provided as part of the base image. Cat it out, and you see I made some changes. Exit the VM, and then I can commit that image, which, if you're wondering where I got the string, just look on the left where you normally see your username at whatever system. You see root at, and then a string of alphanumeric characters. That's called the container ID. So you do docker commit your container ID and then your image name. Now that image is available on your local machine, and you can just run that how you normally would do. So down here at the bottom, we have docker run chd new, which new is the tag that I used, and then give it the command to cat out test.txt, and we see that it works. Everything has been committed, and we are good to go. Additionally, containers can be told to run a script or a program on startup, as you saw with RZA, whether this be done through entry point or command. You can even create what could be a startup.sh script. So when you start up a container, you can have it run that script and do whatever you want the container to do from that point on. And additionally, if you just wanted to mess around with something, maybe try out a new dependency or something like that, these can also be used as a throwaway VM. So you would start up like a Fedora container, try installing different dependencies, see if there are any conflicts or whatever. Basically mess up anything that you would typically be a bit hesitant to do on your local machine, or even a system that you may have gotten through Beaker or some other means. Try things out, see if it works, see if it doesn't. If it works, commit it, you're good to go. If not, you can just escape out and throw it away. Since it's a container, it doesn't really matter. And one of my favorite things about these are that they are very lightweight and very fast. Images typically take up relatively little space, and they usually spin up in less than a second. The performance is, of course, completely dependent on whatever hardware you're running this on. For myself, most images run up in about 0.5 seconds. That's through pretty much every server and also my local machine that I've been testing these things on. The memory usage is typically pretty minimal, but this is again completely dependent on whatever you're running on the container. So if you're just running, a basic script, maybe you're just hitting up an API request or something like that, the memory usage is essentially negligent, or minimal, I should say. But if you're doing something a lot more intensive, like running 20 instances of RZA that are doing a bunch of computations, this can quickly start to consume more and more memory. Again, it's completely dependent on whatever you're running on the container. The typical motto or best practice is to run one service per container. If you want to do other things like linking an application and a database and other different services, it's recommended that you link the containers together, or use a tool like Kubernetes, or less popular now is Docker Swarm or Docker Compose. On the right, you can see the size on disk of each of the images I have in my local system. And the good news about this is that they're not cumulative. So some of these depend on different base images. So for example, I have the Red Hat RHEL 7.4 image, which uses 196 megabytes. But up here, I see a container that is also RHEL 7.4. Since this depends on the RHEL 7.4 image down here, this doesn't actually take up 207 megabytes of space, since it uses those layers that are available here. So it's basically just an additional 11 megabytes of space for that, which is really nice. Okay, so some examples for this. Here is a containerized Apache server, or actually two examples of that. The first one is an alias that I use to just, if I need to serve up something locally, or if, for example, we have a satellite populate job that runs in Jenkins but requires a manifest file, what I can do is just go into the manifest file directory on whatever server I have available at the time, type in the serve me alias, and then it'll spin up an Apache instance on port 1337 in this case, and I can just point that job to this directory, and then the file, the manifest file, it'll pull down and go from there. This way you don't have to worry about actually setting up, Apache on whatever system, and then having it serve up different things from there, and worrying about permissions and all that. Another benefit for this is you can serve up multiple directories on different ports all at once. So if you really wanted to, you could have, let's say, 100 different containers running on 100 different ports, serving up 100 different directories. Not sure why you do that, but you can, and good luck if you do. The second example is a project that I did locally, which serves up a local Puppet repository that is syncable by satellite. This actually does a couple of different things at once. What you would do is when you build the container image, because this also comes with a Docker file, you would put in different Puppet modules into the modules directory. It will run a script upon startup to prep everything. So it'll build the modules.json, create the valid directory structure where it needs to be, and then it will start up the Apache server at the specified port. This way you can serve up a Puppet repository on demand, and you don't have to worry about trying to find different locations other than, at least for satellite, other than Puppet Forge, or maybe if you get lucky, you've got a friend or person on your team that happens to have a few modules on Fedora people. Shout out to you, Agli. Both of these, as you can see, started up in about 0.5 seconds as well, so this is all very quick. All right, stress testing. This is one of my favorite things to do with containers, and they are perfect tools for doing stress and scale testing. And for this, we're going to build on what we now know and use it in the real world. And what I mean by real world is bugs or testing scenarios. So I had a problem with BZ1163452, which is that long API requests were blocking the satellite UI. So I needed a way to easily send multiple long requests to the API. So I just did a bash loop, which used containers as isolated applications to run a curl request with the offending API call to the satellite server. And this is done in with the flag -d, which puts it in daemon mode, which means that it'll create the container within 0.5 or so seconds. It'll move on to the next one, etc., until it's done. So these will all be running essentially at the same time, or within about 0.5 seconds of the one before it. The great thing about this is that since they are isolated, and this can easily be done in a bash for loop, they can easily be scaled up and down. So you can, as I did in the bug, scale it up to 10, 12, 20 some requests all at the same time, and all those containers will just be running at once. You can check out the functionality and then just kill them all or clean it up afterwards. Not have to worry about writing a custom script or anything. And the great thing about Docker, because that's my favorite platform to use, is that you can quickly check individual container statuses with the Docker tail command, which allows you to see any output that the container is putting out. An additional problem, which is something that I focus quite a bit of time on, is that one of the main functions of Satellite 6 is content host management. And many of our customers have well over 10,000 content hosts. Trying to use VMs is way too time and resource heavy to be a viable option for testing. I'm not sure about any of you, but I do not have ready access to the resources to spin up 10,000 virtual machines within any reasonable amount of time to test a bug. So what I did for this is I used containers as mini VMs. I had to account for any peculiarities, which I'll discuss here in a minute. And I used a combination of batch scripting to spin up a bunch of containers, as well as scripts inside of the containers that actually take care of all the registration and any setup that needs to be done, installation, and then even as far as to run Gopher in the foreground to keep the container up and actually retain the ability to run Catello agent, which is what we use to do a lot of our content management on a system. So what I moved on from there is I developed a quick Python script to further automate the container creation and deletion. So for a quick summary in the interim is for containerized host, with some small tweaks, I was able to get containers to register to Satellite 6 as if they were real systems. And effectively, Satellite absolutely considers them to be real systems. And on the next slide, I believe I tell you how I did that. One additional note is that Verizon adopted my solution and is actually currently using it to stress test their Satellite 6. The last time I checked with them was about a week or so after I passed it off to them, and found out that they had already spun up over 6,000 container images and had them all registered to their satellite to test how it would actually work for them in the real world. And the code for this is available at GitHub under my name, and then content-host-d. All right, looks like we've got a recorded thing to see. So let's go ahead and pop this full screen. Here at the top, you can see the command used to run this image. I give it a host name with the -h of test host. I use the -v option to mount the devlog, which is something that is needed for Gopher D to actually run. And then I specify some other environment variables, giving it the satellite host and the activation key. These are things that are used by the script that is currently running inside the container at this point to figure out what to register to, as well as what activation key to use. And at the very tail end, you can see that I'm using the rel74 base image. So going through this output, you can see the registration process with satellite. It downloads the consumer RPM, installs it, uses an activation key rel7 to entitle itself. Nope, let's continue on. And then right now it's actually going through the process of installing Catello agent. Of course, showing through all the metadata that's involved with checking the availability of the package itself. And then hopefully within the next few seconds, it'll manage to install it. Here we go. Okay, now it's got it installed. And I'm not sure what the clarity of this video will be through both YouTube and now BlueJeans compression. So I'm sorry if there's any lack of understanding of what the actual text is saying. All right, so it installed the package, and now it is running Gopher D in the foreground, and you can see that we've got it running, and it's tailing our HSM log. All right, so let's exit full screen and move on to this. So what I mean by accounting for some peculiarities is the first one is that I had to figure out a way to trick Subscription Manager into believing we aren't a container. So here we see a run command, which is just a sed that replaces a particular text in Subscription Manager. I'm not going to show you exactly where that location is, at least not in this presentation, but the code is available on GitHub. That basically just turns off any checking to see if it's a container or not. So effectively, Subscription Manager thinks it's running in an actual machine or a virtual machine, and will register to satellite as if it were. Additionally, the hostname RPM or the hostname package was not included with this version of RHEL 7.4. I think it was actually removed sometime around RHEL 7.2 or something a bit ago. So I just included that in the repository, which was included here when I used the add command in the Docker file to add in the hostname RPM to the temporary directory, and I did a yum local install of that. And from there, I exposed port 22 in case I wanted to do any type of remote execution against the container image. And then finally, we see that the command is running the startup script that we also added as well. All right, so there's a number of different ways you can run these containers. The easiest might be either bash, so that could either be a command line string you pass in. It could be a bash function or a bash script, or as I believe I'll get into in the next slide or two, a Python script as well. I know Red Hat has its own great tools for running and managing containers, looking at you, OpenShift. But this is the easiest thing for me since I don't need to have an OpenShift subscription or worry about doing all the OpenShift stuff on my local machine. I want to try to keep it as clean as possible. So for here, we just have some simple loops. The first one is just spinning up 10 different containers, and you can see the actual Docker command here inside the loop, and this is just running one specific image tag. Now something else that's as neat is that if I wanted to register a RHEL 5, 6, and then a 7 container image to satellite, I can do that as well with bash just by specifying the variable to be 5, 6, or 7, and then I put that in with the I variable at the end here, so the tag will then be 5, 6, or 7. Now, one kind of neat thing down here at the bottom, which is a lovely screenshot of another function that I gave to another customer that was having issues with taking up too much space from the logs, is that you can actually specify log driver equals none. This way you can spin up a bunch of containers and it takes up even less space on your local system. Additionally, DockerPI, which is the primary Python library that I use for scripting with Python, at least for containers, is a pretty decent implementation. But it does allow you to create and control containers fairly well. One of the neat things about this is that you can actually have the script monitor the logs for different exit criteria. What I mean by this is during that script process, we not only had feedback saying that we were registered to the satellite, but also that we were installing Kitello agent and that we were tailing RHSM logs, etc. So you can actually monitor for that text. And in this script, what it'll allow you to do is set exit criteria to be right after registration, kill the container and clean it up. You can also set that for after Kitello agent's installed, just immediately kill it and clean it up, or for a specific amount of time after that. So if I want to have all the errata information on satellite, I'll give it enough time after Kitello agent's installed to do its package upload, etc. Fully check in, and then I will kill it and clean it up. And the great thing about this is that you can run with the script a ton of containers. You can limit how many are running at once. You can specify a max amount, and then you can just leave it to do its thing without having to worry about filling up your system with a bunch of dead containers, which is one of the problems with running it through a bash loop if you don't explicitly include cleanup in that process. Okay, an additional problem is BZ1458857. For this one, we were trying to improve performance of Puppet and RHSM fact importers, and I needed a way to send a ton, and that's a QE ton, of subscription manager and Puppet fact reports to satellite. So my solution for this was to use containers as a mini VM that runs a set script. I built this on top of the content host images that I introduced to you just a few minutes ago. And all I really had to do for this one was just modify the startup script. So for the subscription manager part of it, the containers will endlessly loop fact uploads. For Puppet containers, they will install Puppet and then go through an endless loop of fact uploads. And if you really want to stress test with this, you can just have as many containers as you can run or feel comfortable running on whatever your setup is. The max that you can put on one system is 1,023 at one time, because there is a limit on the Docker network interface of 1,023. If you wanted to do more on one system, you will have to set up a virtual machine with Docker installed inside of them, and then you can do 1,023 of those per virtual machine. And I believe this is how the satellite scale team gets the results that they do, is they have basically that exact same setup. So anyway, you can have all of those containers running endless loops, just constantly hitting your product at the same time, and really determine the performance hit from that. And then we'll take it one step further from what I was talking about with content host creation. So I wrote a Python script that makes testing hypervisor and guest entitlements very easy. Since I don't have unlimited resources when it comes to VMware or whatever type of hypervisor host that you want, I wrote this script so that way it will use one container to send a fake virtwho report mapping the hypervisors and guest IDs to satellite. So it thinks that virtwho's checking in from a legitimate hypervisor host, and it'll accept that. So it will immediately put in all those hypervisors into satellite, the hosts, so that I can go in. The script gives me a bit of time to attach any subscriptions to the new hypervisors. Once I'm good to go with that, I can hit enter, and it'll start the guest creation. And each guest is assigned modified facts. So it will actually use subscription manager facts to give it a guest ID that the satellite is expecting from the previous step, where it sent that the hypervisor and guest mapping to satellite. So each of those would be then expected guests as far as satellite is concerned, and then it will actually register correctly, and you'll see the correct mapping of hypervisor to guest in satellite. This way you can specify as many hypervisors as you want, as many guests as you want. If you want to do, you can do 100 different hypervisors, each of them with 100 different guests, and you don't need to have those massive hardware requirements as well as time requirements to not only set up the hypervisors, but also start up every single guest in VMware or whatever your system is. You basically just use the one script. The containers will then do their thing, and the script takes care of creation and cleanup for you. You can basically just walk away or work on something else and come back to it when it's all done. So this is kind of a call to action. I want you guys to make it your own, whether that be containerizing your testing framework. I've been working on trying to containerize all of Ropatello, which is what we use to test satellite, which I think would significantly increase not only the stability of our Jenkins jobs, but allow us to better parallelize tests so we can potentially get faster times during our automation. You can experiment with different orchestration techniques, whether that be Kubernetes, Docker Compose, Docker Swarm, whatever you want to do out there, even writing your own custom orchestration script like I did previously. You can also integrate it with other technologies such as Ansible. I believe Ansible has its own Docker or agnostic container plugins that are available, so you can run all this stuff through Ansible itself. On the right, I have an Ansible playbook that's set up to install everything that's needed and set up the environment if you wanted to get started in testing my RHEL 7.4 container images. You don't have to worry about installing Docker, pip, all the different requirements up to that point. It'll install that and even go so far as to build the container image for you, so you can just run the playbook, go to the system, and you're good to go. There really are very few limits on what you can do with containers, and I want you guys to expand it out, maybe find those limits, and then push further. An additional note is that containers can be very messy. The first time that I really started experimenting with Docker, I didn't know that it didn't automatically clean things up after I was done with containers. So my system had thousands of dead containers that were just sitting within Docker and actually taking up quite a bit of room on my local file system. I was wondering what was taking up about, I think at the time it was somewhere between 8 to 10 gigs of space on my local file system. And after a bit of research, I realized that it was all the different Docker volumes and container images and dead containers that were still just hanging around that I needed to clean up. So from that, I created a number of different aliases such as Docker Kill, Docker RM, Docker RMI, RMV, which will clean up any dangling volumes, and then route those all into the Docker Clean alias. Additionally, Docker Kill is pretty nice if you're using Bash or Bash loops to spin up a bunch of different containers, and you don't feel like going through and Docker killing each one individually or whatnot. You can just run Docker Kill. It'll kill everything that's running on your system, and then Docker Clean will take care of the rest. An additional alias you guys might find useful is if you're running a container or set of containers in daemon mode. You can just type in detail here at the bottom, and it will tail the first container that's available. So if you're running a set of containers that are all doing the same thing, you can run detail and see how one of them is going to get an idea of how the rest of them are going. Additionally, if you're just using one container at once, it's even better. Detail will just return that one container's logs. All right, so we've come to the end. If you have any questions, any comments, anything you'd like to see me do, or need help with something, feel free to send me an email, hit me up on IRC. I'm available, of course, on the internal channels at satellite6-QE, and also RDU16NE. Additionally, I'm also available on Freenode in a number of different places, but more reliably is Robotello. Again, my name is Jacob Callahan. You can call me Jake. I hope you have found this useful, and I hope you have a good day.